Good morning and welcome to physics class. And I just realized that I didn't put numbers in. Bob Jones doesn't put any numbers on, and I usually try to put them in, and I didn't do that this morning. I might put them in before you see this. If I don't, you can follow along. I'm pretty much going through it, but I wanted to emphasize. I made sure that I got the material I wanted to share with you. What I'm going to do, the way we're going to do this section of chapter 23 is I'm going to talk about it today, and then in our next class, I will go through the review page. There are five math problems that to do, and we'll do those together in our next class, okay? So this class will just be a matter of, you're going to need to get some information out of this, though, because you're going to need this information to do the review page. Okay, so reflection and mirrors. So first of all, what they call ray optics. Now, we talked about the idea in the first part of this chapter that light is a wave or a wave packet, but it also can be viewed as rays because light travels in reasonably straight lines. So you can draw light as a ray of light, like a light source, as lots of rays of light. And light will travel in reasonably straight lines. Now we're going to talk about reflection. Now the other chapter we're skipping talks about refraction, which is where you bend light waves. Reflection is where you're simply bouncing light waves changing direction. Refraction also happens when light passes through something. Reflection bounces off of something. Now, the basic principle of reflection involves a couple of important words. First word is normal, which means perpendicular. We talked about normal force earlier this year. Okay, so if you're looking at a mirror, and we're going to be looking at flat mirrors and curved mirrors, but in any of them, normal line is the perpendicular line. And if it's a curved mirror, if you drew a tangent line and then you drew a perpendicular line, that would be the normal line, okay? The angle of incidence is the angle between the light ray coming in and the normal line. Okay, the angle of incidence is the angle between the light coming in and the normal line. The angle of reflection is the angle between the reflected ray and the normal, okay? So the angle of incident is between the incoming, incident meaning incoming, I don't know if that's what it means, but that's what it is, and reflection is the outgoing ray, the angle between those rays and the normal line. So the law of reflection involves two parts. First, the incoming ray, the normal, and the reflected ray all lie on the same plane. So this is two-dimensional, okay? Same plane. This is a flat situation. And the angle of incidence equals the angle of reflection. This is really important. When it comes in, it bounces out at the exact same angle as it bounced in or came in, okay? So this actually makes life really easy. The law of reflection, God made this easy for us. When light goes in, it bounces out at the same angle. Okay? So, what happens with a plane mirror? Well, first of all, the image we see in a mirror is called a virtual image. And the reason it's called a virtual image is that, a real image, you could actually put a piece of paper up and it would project on it. Well, obviously, if you look in a plane mirror, you cannot stick a piece of paper up and see yourself on that paper. So it's not a real image, it's a virtual image. And what we see is what it looks like. It's behind the mirror. That's what it looks like. Well, obviously, it's not really behind the mirror. It's actually, the light is bouncing back to our eyes, and our eyes interpret it as being behind the mirror. So it's a virtual image. And in a plane mirror, it appears that left and right sides are reversed. And if you think about what's happening, it makes sense. Your left shoulder light goes into the mirror and bounces straight back at your left shoulder. Your right shoulder light goes in and bounces straight back at your right side. Because if you think about this, it's a plane mirror, it's a flat mirror. So if light's going straight in, it bounces straight back. Well, what that means is that your left side is directly in front of you on your left side. But normal people, if they're standing in front of you, when they look towards you, their right side is pointing at your left side. And so that's why we say it looks reversed. In many ways, it's not reversed. The left is on the left and the right is on the right. It's just that we're not used to people doing that. When people are standing in front of you, looking at you, like you look like you're looking at yourself, they are facing the opposite direction, so their right and left sides are opposite of yours. I hope that was clear. If you're using multiple plane mirrors at various angles, you can see multiple images. So for example, if you take two mirrors and put them at a 90-degree angle to each other, you get 3 images. If you take those two mirrors and put them a little closer together so they're at a 60-degree angle, then you get 5 images. If you tilt them at a 45-degree angle, then you get 7 images. And so you can actually get a formula for this. The number of images for a given angle is this formula. 360 degrees divided by theta minus 1. That's the number of images. You want to write that equation down. If you haven't written anything else down so far, you should have been. This definitely write down. N equals 360 degrees divided by theta minus 1. This equation helps you find the number of images for 2 plane mirrors at a particular angle to each other.
So what about curved mirrors? And the curved mirrors come in 2 forms. Concave mirrors, which make a cave, so the light is bouncing off the inside of the cave, and convex mirrors, which bulge out, and so the light bounces off the outside of the mirror, kind of. Now, they're going to talk about this quite a bit. Spherical concave mirrors produce spherical aberration, which is not an issue with parabolic mirrors. And we'll say more about that later. Spherical mirrors, however, the math is easier, so that's what we're going to do. We did do parabolic focus in advanced math, so you've all done that. But you can just be thankful we're not doing that for this particular activity. So the principal focus, or the focal point, and the distance from the focal point to the mirror is called the focal length. Okay, so that's important. The focus of the mirror is highly important for everything we're going to talk about. The radius of the mirror is important for spherical concave mirrors, which is what we're going to be looking at. So for a spherical concave mirror, we're caring about the radius of the mirror as well. So if you imagine the mirror as a concave mirror, but if you continue to make a complete circle out of it, you would get a circle of radius r, okay? And the center of the spherical mirror is the center of the spherical surface. Therefore, the line through F, the focus, and C, the center, intersects the mirror at its vertex, called the principal or optical axis. Most of this is just kind of geographic terms, geographic vocabulary. We'll see this when we start drawing pictures, okay? But so what you've got then is, well, let me get to the pictures as soon as I can. A spherical concave mirror has a focus halfway between the vertex and the center of the circle, okay? The center of the circle, or center of the sphere, and then the vertex, which is what the edge of the sphere, halfway between those two is the focal point. So we have this equation. Another equation you need to write down. The focus point, the focal length, is half the radius. You do need to know that. I'm not going to use that a lot, but we will use it. Okay, I'm going to apologize for this diagram. It has a lot of really cool stuff on it, and I wish it would have given it to me in a way that I could have built it up rather than having it all here at once, because it gets a little confusing. But let's start at the top. So the radius of this sphere goes from the edge of the mirror, the sphere, into the center of that imaginary sphere that the mirror would create. The focal length is half of that, so you can kind of see that relationship. In the middle, you have this line that goes from called the optical axis. If you see that, goes from the vertex, which is on the mirror itself, through the focal point and through the center. Okay, and they're going to illustrate 3 different kinds of rays here that are important to us. So imagine light rays coming in, what they call parallel. These are light rays coming in a straight line, parallel to the optical axis. And you've got 3 of them, and they're labeled 1. Oh, you got 4 of them actually. They're labeled 1. Got 2 near the top, 1 in the center, and 1 at the bottom. And what you notice about all of these, they're coming in parallel to the optical axis, bounce off the mirror, and go through the focal point. You see that? They go through the focal point. So all 3 of these lines go straight into the mirror and then bounce through the focal point. And if you look at where they hit the mirror, you'll see that their angle of incidence equals their angle of reflection. That's our basic rule. Angle of incidence equals angle of reflection. So if you look at those 2 angles, and they have a little dotted line there to show you the normal line. So it's the inside angle that we're looking at. Okay, the angle inside the green angle
where the dotted lines are. We're looking at the angle incident and the angle reflection. They're the same. And the two lines up above, they bounce in, they bounce out, go through the focal point. The line down below, same thing. The line down the middle does also come straight in and bounces straight back out through the focal point. Number 2 is illustrating lines that come in through the focal point will bounce out parallel. So if you look at the yellow line there, it comes down through the focal point, hits the mirror, and when it comes out of the mirror, it's coming out straight. Again, if you look at the bounce point, it does have an angle of incident and angle of reflection. They're the same. There's a number 2 line that goes straight through the focal point also along the optical axis. That's really not that interesting, to be honest with you, but it's there. Okay, so here's the key. Lines coming in parallel go through the focus. Lines that go through the focus come out parallel. Okay? And then the third thing that they show you there with the pink line as number 3 is that any line that goes through the center will bounce back through the center. And we don't use that one much. That rule doesn't get used much, but it is there. If the line goes through the center of the sphere, it will bounce off the mirror and come right back out. That's because it's going to hit right along the normal line. It's going through the center of the sphere. It's going to hit normal line. So the angle of incidence is 0, so the angle of reflection is 0, so it comes straight back through. Okay, so that kind of shows you what do we mean by focal point, center, vertex, etc. Now, they give you some definitions. The object distance is the distance of the object from the mirror. The image distance is the distance of the image from the mirror. They just chose a weird font for that I. But anyway, okay, so these are kind of straightforward, kind of obvious, but you have to use these terms. So object distance, d sub O, is the distance the object is from the mirror. Image distance, or d sub I, is the distance the image is from the mirror. So, there are 6 possible cases with the object located on the optical axis. Now, they give you another definition. We're going to talk about all 6 cases in just a moment. A real image is one which can be focused on a screen. I said that earlier, and that's always going to be in front of the mirror. So if it bounces off the mirror, you're not going to look in the mirror and see it. You're going to hold a piece of paper out in front of the mirror and actually see the image projected on that paper. Okay, that's a real image. If it's a virtual image, you're going to see it in the mirror, look like it's behind the mirror. So now let's look at examples of how the reflection works in a concave mirror. And then we're going to talk about the math afterwards. Okay, the equations are later. Right now we're going to draw pictures. Okay, and they start with what they call case 2. This is where the object is beyond the radius of is farther away from the mirror than the radius, so it's behind the center. Now, look at what's happening here. This is actually just drawing arrows. Makes sense, but you have to be careful, okay? So what we do is we follow 2 rays from the top of the image, and we use ones for these images, like a concrete 3-dimensional 1, and we just take the top of the 1, and we draw rays, and that tells us where the top of the image is going to be, and then we draw the image down from the top to the center line. So we take this 1. Now the first ray, going from number 1, green ray, goes in parallel. It's going straight in from the 1 to the mirror, and that means it bounces through the focus point. And so we draw it straight in, and then we draw it through the focus point. You need to draw fairly straight lines for these to work. Number 2 is going through the focus point. So it leaves number 1, goes straight through the focus point, but that means that it's going to bounce out parallel to the optic line there. Where those 2 lines cross is the top of the 1. Now please notice that it is upside down, it is in front of the mirror, which makes it real, and it is smaller than the original. So if you are standing behind the radius of the outside the radius of the mirror, your image is not going to be something you can see in the mirror. It'll be dangling down in space. You need to have some sort of elevated spot to make this work. And you'll be upside down. You'll be about half your normal height in this particular image. And you will could be projected on a screen. You actually wouldn't see that image, I don't think. You'd have to put a screen there to project it onto the screen. Okay? That's what they call case 2, where you're outside the center. Then they skip to what they call case 4, where the item is between the focal point and the center or the radius. Okay, so this is this image, and you see there it is between the focal point and the center. Again, we draw ray number 1 goes parallel to the optic line and bounces through the focus. Line 2 goes through the focus and bounces back parallel. Where they cross is the point of the 1, and you see that this is an upside down 1. You see it as a larger than the original, and it is an image. So if you had a screen there, it would project onto the screen. It's in front of the mirror. Okay? Are you with me so far? Yeah, I hope so. If not, you're out of, if you're not, just go back and re-listen to it. Look in your book also. The book does the same thing I'm doing. Case 3 is where it's sitting on the radius. If it's sitting on the radius or on the center, again, this is the same in every single one, just the lines go different places. Draw a straight line from the top of the 1. This is line number 1, green line. Parallel in, bounces through the focus. Number 2 goes through the focus, bounces out parallel. Where they cross, what we get then is a perfectly upside down image, a real image again, exactly the same height as the original, and the same distance from the vertex. It just flips it upside down. So if you were standing on, say, some sort of a platform, like a glass platform, let's say, and you were standing in front of a spherical concave mirror, and you were standing right on the center of that radius, you could look down and they could put a screen there, and you would be sticking, your image would be straight down, feet to feet, and head down. All right, case 1, this is where the 1 is an infinite distance from the mirror. And you'll notice that line 1 goes parallel and hits the mirror and bounces back. Line 2 is coming in from a really, really long distance, but it technically goes through the focal point parallel also and bounces back through the focal point, which means that you end up with effectively no image at all. It's a pinprick at the focus. And the problem is that both lines are basically coming in parallel. One is coming in parallel at the height of the 1, and one's coming in parallel along the focal point. And so they both bounce back through the focal point, and they're just together. There's just no image there. The 5th case is when the object is sitting on the focal point. And what happens here is that the two lines never meet. You'll notice the green line number 1 goes straight to the mirror and then bounces off through the focal point at an angle, whereas the yellow number 2 goes straight through the focal point and never gets to the mirror. And so these two lines never meet each other, so there is no image at all. And then case number 6, and this is where the image is between the mirror and the focal point. Now this one gets a little weird, but look at how this works. The green one, the green arrow, number 1, goes straight into the mirror and then bounces out through the focal point. And it just goes out through the focal point. You can see that. Line number 2, now it doesn't actually go through the focal point, because if it did that, it wouldn't go to the mirror. So what it does is you follow a line from the focal point through the top of the 1 and then to the mirror. If you follow, you see the dotted line and then the yellow line, and it hits the mirror and it goes straight out. So it's not going, technically it's not coming from the focal point, but it is. It's coming at the angle it would come at if it were coming through the focal point and through the top of the 1. Now they add line 3 because this is weird, and this is going through the center line. It goes parallel. It's the line that would go straight through the center and through the top of the 1. So they give us 3 lines on this one instead of only 2. Now, all 3 lines coming out to your eye or coming back towards you do not meet together. Therefore, they don't form an actual image. What your eye does is it assumes that these 3 lines, 1, 2, and 3, are coming from an object. And so it projects backwards and says, oh, that object must be in front of the mirror, behind the mirror, at that point where those 3 lines would converge if they went back. It's like your eye says, here are the lines coming at me, and it projects backwards. Where must they have come from? And it ignores the mirror and puts the image behind the mirror. So this is a virtual image. You actually would see this. If you're looking in the mirror, you would say, oh, in the mirror, I see me taller. Maybe you'll see that that the image is actually taller than the original. So you say, oh, I see me and I'm taller, but it's a virtual image, okay? It's not a real image. but your eye interprets it as an image. Okay, so it's kind of bizarre, but that's what happens with a plane mirror all the time. Okay, so that's the drawing part of it. Okay, we're going to do some more drawing when we do the review page. Now for numbers, okay? Equations. First one is the mirror equation. You need this mirror equation. This is another thing you need to write down. If you're not writing anything else down, you do need this equation because you'll never make it through the review page without this equation. 1 over DO plus 1 over DI equals 1 over F. And I will just mention, we've got this reciprocal equation. It's kind of like parallel resistors from the previous chapter. And one of you, I don't remember who it was on the test, when you got to the end of this, you had a 1 over F equals something, and then you just wrote that down as the answer for F. Okay, it wasn't F, it was 1 over R at that point. If it's 1 over R equals a number, R doesn't equal that number. You have to do the reciprocal. So we're going to be dealing with reciprocals and fractions in these, okay? And if the distance is behind a mirror, then it's a negative number. Okay, cool point. If it's a negative distance, that means it's behind the mirror. It's a virtual image behind the mirror. Now, magnification has to do with how much does it go up or down? How tall is it? And the equation that we use is HI over HO equals the negative of DI over DO. So the ratio is determined by the ratio of the distances, but the negative sign means that actually has to do with flipping it. That's why you'll notice all of the images we had were upside down, so you're going to get a negative height because they're pointing down, except for the virtual image, because there you've got a negative distance. Because you have a negative distance, it makes it a positive height, and so it's actually goes up the right direction. And then magnification is just that ratio, the absolute value of the ratio between the image height and the image object. Or the image height and the object height, excuse me, not listening to myself very carefully. Image height and object height. Okay, so those three equations, you do need those three equations, okay? You need, this relationship of heights to distances, and this, you need the magnifications, okay? Okay, just a couple of comments about spherical versus parabolic mirrors. In a concave spherical mirrors, not all incoming rays are reflected, so they actually pass through the focal point. We assume that. Reality is, it doesn't quite happen. They go real close to the focal point, but not quite, and so you end up with a little blurring. And the flatter the mirror, the larger the radius, the better you get. But you do have this problem. A parabolic mirror, that doesn't happen. A parabolic mirror, every single ray goes through the focus. And if you remember when we did parabolic equations in advanced math, we learned about the focus. And we learned how to find the focus and the axis of, what was that thing called? Y equals something. I can't remember what they called that now. Anyway, we found those. But we're not going to deal with those, any math with those or any diagrams with those. Parabolic mirrors are going to be very similar to spherical mirrors. Math is just a little different. All right, that covers the information. What we'll do on the review page then is to practice actually doing some of these, okay? All right, well, have a good day, and we'll talk again.